Problem 11.115 involves a sprinkler that's watering over a crop. We're going to look at two scenarios, the maximum distance that the water can hit if the crop is low, and then the other time is when the crop is a little high. The water coming out of the sprinkler is at 8 meters per second. This distance here for the highest and closest corn stalk or whatever this crop is going to be 1.5 meters. And then H is going to be this height out here, which is going to be 1.8 meters. In the A part, we're to find what is the maximum value or maximum distance the water can go. When the crops are low, it doesn't have to worry about hitting anything. So we're to find D and alpha when the growth is low. D is to be the maximum value, in other words, and this is the value D across here. So it's the range of the water. We can look at x equal to v naught cosine alpha times time. That's the initial velocity in the x direction times time. X is going to be my d. And we solve for t out of that. We get d over v naught cosine alpha. We're going to plug it into the y motion equation just like we've done in class and other problems. And when we do, this reduces down to y is equal to d tan alpha minus gd squared over 2v naught squared cosine squared alpha. That's going to be called equation 1. For y equals 0 in this equation right here, then you've got a quadratic, but there's no constant term. So you can do a factor out. Either d is equal to 0 or this term right here, tangent alpha minus gd over 2v naught squared cosine squared alpha is equal to 0. So you get two solutions, d equals 0 and d is equal to this. Well, it makes sense. I mean, d is equal to 0 when y is equal to 0, and d is equal to this other value when it's over here. So that's equation 2. And by the way, that reduces down to you're going to have a 2 sine alpha cosine alpha, which you'll combine into sine 2 alpha. Well, you can take a look at this one's easy to maximize because you can see that d is going to be a maximum when sine 2 alpha is a maximum. And the maximum of the sine can be as 1. And that would be 90 degrees. That means alpha would be 45 degrees. So we plug that in here and you get a d value of 6.52 meters. The next thing is to find the d value and alpha value that will clear this point B and H. D is to be, again, a maximum. So BH is B and H high. Okay. Equation 1 then becomes, we're going to take equation 1, you plug in H for Y, you plug in B for the X value, and tan alpha and minus G X again is B squared, 2V naught squared. And when you write this out, you can rewrite the cosine squared as a secant squared like this, because 1 over cosine squared is secant squared. And secant squared is 1 plus tangent squared. So what happens is this equation right here will simplify down to a quadratic expression that looks like this. And you can pause here and try to create that expression yourself. But it has solutions of 81.96 degrees and 58.2 degrees. Since we know 45 degrees is going to give us a maximum, then alpha higher than that is going to keep getting shorter and shorter distances. So we want an alpha that's closest to 45 degrees, and that would be this one here. So you plug that back into equation 2 right there and calculate your new d value, and you get 5.84 meters.